Hello everybody, and welcome back to the signal processing playlist. I'm Lorenzo, and today we're going to build together the theoretical basis you'll need to perform any kind of signal processing analysis, both in time and in frequency domain. In this video, we will go through some definitions such as the sampling time and the sampling frequency, and we will get some practice with it. Then we will move to Aliasing and the 90s theorem, and we will run an app in Compose to better understand this concept. And at the end, we also briefly introduce the frequency resolution. To do so, we're going to leverage the Compose notebook, which is an extremely powerful tool where we can mix text with pictures and with editable scripts. So, for those of you who feel already confident with these topics, please take this video as a chance to get familiar with the notebook. But as mentioned before, we are also using the regular Compose to run an app. Hopefully at the end of this video you will get a good understanding on how the discussed parameters will affect the signal representation both in time and in frequency domain, and how to properly select them, for example, to avoid aliasing. But let's start, and let's open the notebook. If this is the first time you are opening the notebook, I will give you a few instructions on how to use it. So probably the first thing you want to do is to change the name of your document, and I will do it here. So I'm changing to my first notebook. After that, you want to create your first cell, for example a text cell where you can type some text. So we are going to select markdown cell, and we are going to type something. After that, maybe you want to add a coding cell. So I'm going to select the code as a type of this cell. And I'm going to type some code. For example, here I'm going to ask to print out a string, the one that I'm typing. And the best part of the notebook is that you can edit as you wish your scripts. So here I'm going to change the string and I'm going to rerun the code. And we'll get a different string. The other commands you need to know are all gathered in this toolbar, and you will see that you will become familiar pretty soon with the notebook. But now let's move to the lecture. So the first topic we are going to discuss is sampling time, and as everyone knows, the computers works on discrete data, and the sampling time defines how we move from a continuous signal to a discrete one. So let's look at this picture. If we have a continuous signal, we can record its value at some space-time instance, and the distance between two successive samples is defined as the sampling time, or as the sampling period, which is indicated with the capital T in this picture. And if we compute its reciprocal, we get the sampling rate, which is also known as the sampling frequency. But let's have some practice with it. And let's solve this first example. Our goal here is to plot a 6-Hz cosine wave. So I'm going to insert a new cell, and I'm going to type the signal expression as the one written above. If I run this script, of course I will get an error because we have neither defined the frequency, neither the time. And I'm going to do it here, so the frequency is 6 Hz. While to define the time, I will go to define before the sampling time. As a first choice, I will set it to 0.01 second, and after that I can define the time array, spanning from 0 to 1 second. As you can see, this script runs successfully. The last thing I need to do is to add the plot. I will do it with the plot command, and I will ask the notebook to show the plot with the show command. But before doing that, I can also add a label on the x-axis. If I run this cell, I will get the plot. As you can see, we get a signal which is kind of smooth, but I want to try to have a smoother signal. So what I can do is to decrease the sampling time to 0.001. And now you can see that the signal is really smooth, and it looks like a cosine. Instead, if I increase the sampling time to 0, 1, what I get is a signal which is not smooth at all, and we cannot even recognize that it's a cosine, even though we are still plotting a cosine. What we've done so far could have also been done with the sampling frequency, and we'll do it here. So I'm going to define the sampling frequency. As a first choice, I will set it to 128 Hz. With the sampling frequency, I can use the formula I showed you before to compute the sampling time. And the rest is the same as before, so I can just run the script and get the plot again. The signal is pretty smooth, so we have an accurate representation in time domain. What happens if we are increasing the sampling frequency? The signal gets even smoother, and instead, if we decrease the sampling frequency, we get a signal which again is not smooth at all, so the accuracy in representing it in time domain is pretty low. So what we're seeing with this example is that increasing the sample time or decreasing the sampling frequency with respect to the frequency of the signal, we get a representation in time domain which is not that accurate. And this conclusion was pretty obvious. But what happened with the frequency content of the signal? Well, if the signal is undersampled, and we will clarify this term in a minute, the frequency content of the signal gets corrupted. And what we are perceiving is another frequency called alias frequency. And this unwanted effect is known as aliasing. A common and practical example of aliasing is when you are watching racing cars driving in one direction while their wheels seem to spin in the opposite direction. And in this case, the sampling frequency of the camera is too low with respect of the spinning frequency of the wheels. So, is there a criterion we can use to define the lower bound for the sample rate in order to preserve the frequency content of the signal? Well, yes, and the Nyquist-Shannon theorem helps us to do that. And in fact, it states that the sample rate has to be at least twice the highest signal frequency. Hence, we can define the Nyquist rate as the minimum sample rate which satisfies the Nyquist theorem, while the Nyquist frequency is defined as half of the sample rate, and it represents the frequency of the signal which doesn't generate aliasing, giving that sample rate. But now let's recap this important concept with an app we built in Compose. So let's open Compose. We are leaving the Compose notebook for a while. And through the command window, we can run this app. We can see that there are two plots. The one on the top is representing the signal in time domain and is the discrete representation, while the one on the bottom is used to draw some frequency information, such as the signal frequency, the sample frequency, and the Nyquist frequency, and later also the aliasing frequency. Then there are two sliders. The one on the left is used to vary the signal frequency, while the one on the right is used to vary the sampling frequency. As done before, let's consider a cosine wave of 6 Hz. As a first step, let's increase the sample frequency. While we increase the sample frequency, we can see that we are adding more points in our time domain representation, so the representation of the time domain signal is more accurate. If we can imagine that we are linearly interpolating the signal between two successive points. Instead, if we move the slider on the other direction, we are decreasing the sample frequency, and we are also decreasing the number of points used to represent the signal. So the time domain representation, again, supposing that we are using a linear interpolation between two successive points, is less accurate. Let's get to a sampling frequency of 12 Hz. At this sampling frequency, we can see that the time domain representation is not that accurate. In fact, we are representing our cosine wave as a triangular wave. But instead, in frequency domain, the frequency content of the signal is completely preserved. the triangular wave will have a frequency of 6 Hz, the same as the one of the cosine wave. In fact, if we look in frequency domain, we see that the 90s frequency, which is half of the sampling frequency, is exactly the same of the signal frequency. So we are still able to see the frequency of the signal. And now I'm encouraging you to pause your video here to think about what is going to happen if we further decrease the sampling frequency. I will do it here. So if we decrease it, what we see is that aliasing occurs. And if we decrease the sample frequency, also the aliasing frequency will decrease. So for example, for a sampling frequency of 10 Hz, we are perceiving a signal at 4 Hz with respect to the 6 Hz of the original signal. And if we further decrease the sampling frequency until 6 Hz, which is the same frequency of the original signal, we can see that the perceived frequency is equal to 0. So we are perceiving a constant signal, while our original signal was at 6 Hz. And if we decrease further the sampling frequency, we can see that this time the alias frequency will start to increase. And for example, let's bring the sample frequency to 4 Hz. We will see that the alias frequency is 2 Hz. And now what is interesting is that if we increase at this point the original frequency of the signal, let's do it together, and let's bring it to 10 Hz, for example, we see that we are still perceiving a frequency of 2 Hz. So due to the aliasing effect, we are no more able to distinguish two signals with two different frequencies. And that's it for this example. Let's move back to the Compose notebook. The last thing I want to talk about is the frequency resolution. The frequency resolution can be thought as the sampling time in the frequency domain. So it is the distance between successive frequency beams in the frequency domain. And it also represents the smallest frequency we can visualize. Here there is the formula on how to compute that. So we can see that is depending on the length of the acquisition time. But let's try to compute it for the same example I considered before, the 6 Hz cosine wave. So let's redefine the sample time and the time array. Let's type the formula for the frequency resolution. If we run this code, we will get 1 Hz, since the length of the acquisition time in our case is 1 second. We are starting from 0 second and we record the signal until 1 second. If something about the frequency resolution is not clear, don't worry, because everything will be clearer when we compute the FFT. But we are going to do that in a dedicated video. That's it for this video. I hope you enjoyed that. Before leaving you, let me remind the last useful information. In the Model-Based Development Forum, you will find all the material for this lecture, and feel free to ask any question you have. I will be glad to answer all of them. Thanks for watching.